Okay. All right. So yesterday, where we finished off was by recognizing that due to the specific quantum states that the dark matter, ultralight dark matter is in, you can just think of it as a classical background, right? That the coherent states, and that's exactly why. And so today we're going to talk a little bit more about some overall strategies on detecting ultralight dark matter. And then I'll actually speak a little bit about the strong CP problem, which is a big motivation for a number of these dark matter candidates. Okay. Okay, the bottom line from yesterday was the following. I think that the dark matter is the ultralight particle, ultralight boson, and it effectively amounts to me saying there is some classical field, okay, in the universe that I want to detect. And if I think there's a classical field, there's a classical boson, the way we generically would describe it is to say there is some classical field phi tx, okay, and it has some amplitude phi naught, and it's got some oscillation omega t minus, let's say, k dot x. Okay, that's how I write this classical field. And I want to compare this with the typical electromagnetic field that you might have written before in your life, where you say there's an electromagnetic field, E dx, and you say there's an amplitude E naught, and you might say there's a cosine omega t minus k dot x, once again. So there are some similarities and some differences because the dark matter is a non-relativistic particle, right? The similarity is the fact that phi naught and E naught, these represent the amplitude of the field, okay? And therefore, from that you can extract the energy density in the field, right? The big difference between the two is the fact that since the dark matter is a non-relativistic particle, its frequency and momentum have a velocity dependence in them. So specifically, k is basically mv, right, equal to mv. Whereas for the photon, omega, the absolute value of omega is equal to the absolute value of k, right, because it's a massless particle. That is the one big difference. So now we want to talk about the problem where we want to say if this kind of phi is the dark matter in the universe, how do I detect it? Okay. So detecting it means it's a lot like thinking about how we would detect a radio wave, where the way we detect a radio wave is to basically design some kind of antenna, and a radio wave comes by, and this radio wave is going to move charges up and down that antenna, and you measure that somehow, right? So if you want to think about detecting this guy, you must first understand a little bit about some of the properties of the electromagnetic wave that's coming in. So what you'd want to know for a radio, for example, you'd want to know what frequency the radio actually is in, right? Because you want to listen to a specific radio station, you want to tune something, so you need to know the frequency. So for the dark matter, the frequency is going to basically be set by its rest mass energy. So this omega here is the frequency of the wave. For dark matter, we would say, okay, what is omega? It's a non-relativistic particle, so omega is basically equal to the mass of the dark matter. So I'm going to be looking for some time-dependent signal that's going to be oscillating at a frequency equal to its mass. Okay. The second property you need to know to detect anything of this kind is you need to know for how long do you expect to receive that signal at a specific frequency. So for example, if I am, I don't know, communicating with you on these radio transmitters, right? And you have your radio receiver, you're trying to receive that transmission from me. Even if you know what frequency I'm sending you that signal, you should know when I'm communicating with you or for how long I expect to be communicating with you. So what does that correspond to in the case of the dark matter? We basically have to ask, well, the dark matter is around us at all time, of course, so it's always communicating with us. But the question you want to ask is basically, is it always communicating with us with a known phase? Okay? What does the word known phase mean? Well, basically, for how long can I reasonably write the field in the simple way as a cosine omega t minus k dot x? Okay, how long is that true? And so let's think a little bit about where this kind of dark matter is produced. I won't say too much about it because Marco will cover it in more detail. But here is the main point, right? We would think that in the very, very early universe, when these kinds of fields are produced, the general idea is that there is some initial value for this field in the beginning of time. And as the universe expands, the field gets extremely homogeneous. It's very, very constant everywhere. Okay? But today, what we're asking is, I'm trying to measure this field in the galaxy. And the galaxy, the dark matter is very complicated, right? When you actually form the galaxy, the dark matter collapses, there is gravitational collapse, all kinds of stuff going on. So today, we would think that the dark matter field is a very random field, okay? Now, even though it's a random field, I can still ask some statistical properties about this random field. I can basically ask the question, look, the dark matter has some field value here at this point. Let's call this some phi naught, cosine delta, okay? It has some phase over here to start with for some random time t and some position x. And what I can ask is, how far do I have to go in physical space before the field value changes by something I don't know anything about at all? Something becomes totally different, becomes totally random, right? That's what we want to know. So we can calculate what is called a coherence length, okay, or a correlation length. Now, I want to emphasize that this word coherence is different from the coherence state we were talking about earlier, right? Because again, this word keeps being used in different ways, but they mean different things. So this has nothing to do with the quantum coherence of the state. All of these states are quantum coherent. They're the coherent states of the quantum field. It is just that even though they're coherent states of the quantum field, they have, let's say, a different correlation length. That is, as you go from place to place, the field value can change. Okay? So in practical terms, what does that mean? Let's go back to the radio station, right? Let's say you are in a world with a very large number of radio stations, and all these radio stations are sending you radio waves all the time. Okay? And that means as you move from place to place, if I just simply sit there and try to measure the electric field, I will get destructive and constructive interference, all kinds of things will be going on. Right? So you would say if I'm getting lots and lots of radio signals, there is basically for any particular radio station, there is some length over which you can receive that signal cleanly, beyond which it just becomes noise. Right? The bzzz that you actually get when you're far from your radio station, it's kind of that thing. So similarly, the same thing is true with the dark matter also. We would say, look, I've taken this field, it's in the galaxy, gravity has messed it up. And so because gravity has messed it up, it's going to be the case that as I walk away from any particular point, if I go far enough out, the field will have a completely different value that I don't know anything about at all. So we can ask, okay, what is the minimum correlation length the field should have? Okay, the maximum, maybe you can be very optimistic, and some people in the field are very optimistic about it, but let's be like asking the question, what is the minimum correlation length that the field should have? How do you estimate the minimum? Well, the way to estimate the minimum is to observe the following fact, right? If I am moving in space and the field value has to change, that corresponds to the field having some momentum, right? Because if this field has no momentum, by construction, the field value is always coherent over all space. Okay? So the existence of a finite correlation length or a non-zero correlation length, the existence of a non-zero correlation length implies momentum in the field. And we know that the maximum momentum the dark matter can have is set by the mass of the dark matter times the velocity of dark matter, which in the galaxy is about 10 to the -3. Right? Basically, if the dark matter had a larger momentum, larger velocity than 10 to the -3, it cannot be bound to the galaxy. It'll get kicked out. Okay? So dark matter momentum cannot be larger than m times this v of 10 to the -3. And that tells you that the correlation length, again, look at this formula, what you want to ask is basically, if I send x to x plus some L, right, how large can L be before the phase completely changes by order 1, right? And the largest that L can be is basically given with the relation k times L is order 1, or in other words, the L is basically less than or equal to 1 over k, okay? And k, we know, is no bigger than the mass times the velocity, and the velocity is 10 to the -3, right? That therefore tells you that the minimum correlation length you must have, okay, this L is basically less than or equal to 1 over m v, okay, which is v is 10 to the -3. Yeah. I really was thinking you were going to say greater than or equal to. Oh, greater than or equal to, sorry, yeah, sorry. Yeah. Sorry, messed that up. Okay. Now, for an experiment, what you care about is not just the correlation length. What you care about is basically how long can you sit there and measure a signal, right? And that's a statement about time. You want to say, look, I'm sitting here, I want to measure this field phi. How long can I actually sit and do so before the field changes dramatically? And so what you care about is basically saying, look, the field has this correlation length L, which is greater than or equal to 1 over mv, and I want to move through that correlation length, right? I'm physically moving through it. That is a minimum time that I actually have, right, to actually measure this, okay? And so we would say, what is the speed with which you are going through this thing? Well, the speed is also v, right? That's a relative velocity in u in the dark matter. Therefore, we say time is basically 1 over mv squared. And since v is 10 to the negative 3, you realize that time is 10 to the 6 over the period m. Okay, so every one of these dark matter experiments will be talking about building some kind of resonance system, whatever, with a quality factor q of 10 to the 6. This is where it comes from. It comes from saying that, look, I expect the dark matter to at least have this correlation length in the galaxy. And whereas this correlation length in the galaxy, I can sit there and measure the signal for 10 to the 6 oscillations, 10 to the 6 periods, because each period is 1 over m times long, and that is how long I actually expect to have before the field changes by order 1. Okay, so that's where the parameters come from. All right. So our problem now is reduced to the following. We have some classical field. Okay, there's a classical field oscillating at an unknown frequency. This is a problem. I don't know the mass of the dark matter. Every single dark matter experimentalist in this business, who after we have a few glasses of wine will be like, hey, can you tell me what the frequency is? Yeah, I wish I could, all right? That's the problem. So it's oscillating at an unknown frequency, which is equal to the mass of the dark matter. Okay, and for a time t, which is 10 to the 6 times the period, right? So that's the problem we have to detect. Okay. So now comes the question, okay, that is the kind of classical field out there, and I want to detect it. Okay. Now we can do, in fact, we will do both these things. One is we can ask the question from the perspective of theory, right? If you're a grand theorist, you go and say, what are the kinds of operators that I can have in the world which will give rise to detectable signals? Okay. And that's an important thing, and we will talk about that because indeed, you know, we discussed this yesterday in terms of technical naturalness, right? Like when I asked you guys if you will fund me to find a nuclear level that's 10 to the minus 22 eV above the ground state, all of you said no, right? So if you're trying to measure really light dark matter, you want to be sure there are strong theory motivations for why they might exist. So the theory is important, and we will talk about that. But before we get to the specific theories, I just want to ask the question, look, no matter what the fancy pants theory is, if you are going to detect the dark matter, at the end of the day, this dark matter has to affect particles that you have in your lab. How can this dark matter affect particles in your lab? Let's just classify that, right? And once we classify that, we can then ask the question, what kinds of dark matter theories give rise to those specific effects? So let's be experimentally guided first, and then we get to the theory. So let's ask the question, how can a classical field impact particles we have in the lab? All right, so let me ask you guys, what particles do we have in our lab that we can control and use? Photons, okay? Huh? Atoms, okay. So we've got photons, we've got atoms, which I will actually separate out. I will call this as nuclei and electrons. Okay? Those are the three particles we have. We also have neutrinos, but okay, I mean, you know, dark matter is already hard. Neutrinos are hard or squared, right? So we will ignore neutrinos from now. All right, so I've got photons, nuclei, and electrons. How can a classical field affect these three particles? What can a classical field, for example, do to a photon? Compton scattering. Yeah, so that's more like a particle scattering kind of thing. Right? So we're thinking about more like a classical field. So what would the way of saying that be? Yeah. It can mix. Yeah, indeed. Okay. So you were paying attention to Kira's lecture yesterday. See, someone was listening to Kira. Indeed. So one thing you can do is that a photon, because it is a very light particle, right, massless particle, is actually possible for the dark matter field, because it's also very light, to mix with the photon, to create a photon somehow. Okay, so let's talk about the photon. One thing you can do is basically you can create a photon, create / mix with the photon, with dark matter, right? So the dark matter can produce a photon or somehow create it because it's very light. What else can the dark matter do to a photon? Phase of the photon. Very good. So what is the yeah, actually by phase you moved your hand also. So I want to know what you meant by the word phase. Polarization. Very good. Great. So the photon has a polarization, and the dark matter can change the polarization of photons. Okay? Change polarization. What else can it do? The direction. Okay? You can change the direction of the photon. Coherent state. Yeah, so basically, since Kiera already gave her talk, that's what she's doing, right? She's basically saying there is a classical electromagnetic, so there's a classical axion thing, and then you put a magnetic field, for example, and then that will become a classical electromagnetic wave. Okay, yes? Yeah, so there's a wave, let us say, and maybe the photon is sent this way, and maybe it moves in some other direction. Just deflection, right? Yeah, like gravity, for example, bends photons, right? That's again a classical field that does it. Okay? All right. What else could it possibly do to a photon? Reduce the amplitude. Okay. Okay. Well, yes and no. Okay, but there's something I'm working on right now, so I will mention it. Okay, it's an interesting possibility. It's not something explode. Okay, so reduce amplitude. Okay, anything else? Yeah. Slow it down, change the speed. Okay, sure. But that's kind of degenerate, I would say, with sort of changing direction, right? Because it's like effectively giving the index of refraction. Well, yeah, sure. I mean, you go through a medium, slows down, right? So dark matter breaks Lorentz invariance because, in a sense, it's a background, right? So you look surprised by this, but when I send light through a medium, it does slow down, right? So, huh? Photon can have an effective mass. Yeah, that's right. Yeah, yeah, yeah. That's right. So indeed, yeah. So maybe let's call it like both those things are essentially index of refraction. Right? So all of those are things you can do to photons. What can the dark matter do to nuclei? So let's put a box here. What about nuclei? What can dark matter do to nuclei? Electromagnetic field, yes. The dipole moment of what? Okay. Yeah, before we get to the dipole moment, right? Just thinking about simple things about the nucleon. So what are observable aspects of a nucleon that you can detect? Spin. What will you do to the spin? Yeah, so this means spin precession, right? Right. So your nuclei have spins, and the dark matter may be able to cause the spins to precess or move around. So you can cause spin precession. And you also mentioned momentum. That is, you can kick the nucleus, right? Make the nucleus move. Now, precisely because nuclei are heavy and there's conserved baryon number, right? For ultralight dark matter, which is extremely light, it's not going to be possible for the dark matter to mix with the nucleon and do any of that kind of stuff, right? So a bunch of stuff that is on the photon column don't really appear in the nuclear column precisely because of the fact that nuclei are heavy, right? And the whatever you can do the nucleus, you can also do the electrons. So electron has spins, you can make the spins precess. You can also move the electrons around. Moving the electrons around, we just call that a current, right? So both these guys pretty much have the same sort of observational effects. Okay? So broadly speaking, you can ignore pretty much all the theory motivations that people go talk about, right? Like the lectures on what candidate of dark matter gives, whatever. If you're an experimentalist, you can take a very practical point of view, and you can say, ignore the theory, guys. Let me think about ways in which I can measure properties of this sort. Okay? And the challenge is the following. The frequency of the dark matter is unknown to me. Okay? The frequency can range anywhere, as we said, from 1 electron volt all the way down to 10 to the negative 22 electron volt. It's a large range of frequency. So it's very difficult for any one experiment or one technology to be able to measure all of these effects in just one shot, right? That's not possible. So what you need to think about, broadly speaking, is essentially, look, I have this very large range of possibilities. What kind of experiments can I realize that will cover different frequency bands? Some experiment will work for 1 hertz, some will work for 100 hertz, some kilohertz, whatever. And what you can make use of is the fact that the signal should last 10 to the 6 oscillations, okay? And that is important primarily from the perspective of combating noise, right? Because every experiment you're trying to construct will have to confront the fact that there is experiment being done in the world, so there's all kinds of stuff going on. So how do you distinguish your dark matter signal from some other spurious source of noise? What you make use of is the fact that the dark matter signal will be at some frequency. The frequency you don't know, but once you find it, you can just sit there and keep seeing that the signal is persistent. And each time you measure that signal, it's persistent for times that are order 10 to the 6 over m, after which it loses coherence. But then, that's what you do. Okay? So that is the observational plan. Any questions about this? Yeah. Yeah. Well, so the question of whether you can use resonance depends a lot on what frequency you're in. Okay? So for example, at 1 hertz, you can build a resonator. But if the dark matter happens to have a mass of 10 to the negative 22 electron volts, which actually corresponds to the lowest mass the dark matter could have, that frequency is 1 over year, right? So you can't really do the experiment for 1,000,000 years, right? So indeed, I was being perhaps a little glib by saying you can always do this, but how much of it you can realize depends a little bit on the frequency. Now, for most of the mass, right, for most of the parameter space, is not an issue, because if the frequency is 1 hertz, you can do an experiment for 10 to the 6 seconds. That's fine. But the lower the mass gets, the more challenging it becomes. And that's typically the case, that in pretty much every experiment you do, lower the frequency, the more difficult it is to combat systematic sources of noise. So you've got to think about cleverer ways of getting around it. Yeah.
So you say we have to explore, we need a exposure for a fixed band.
Yeah.
But how are you sure? For example, here we have, let's say, a 10 power 6 oscillation.
Yeah.
I detect a signal.
Yeah.
I have like 3 kinds. One is 10 to the power 4, one is 10 to the power 6, one is 10 to the power 8.
Yeah.
Now, how do I know which one is the dark matter?
Well, so the thing is, like, if you are in that situation, what you definitely know is that you're seeing noise, right? So what you can do is you can just wait for some time, and if the noise is something in the world, it will go away, right? Like, if it's the noise is due to a train that runs every whatever, right? So go and do the experiment at night. The dark matter will be persistent. It'll always be at that specific frequency. And so you have to be a little careful about what I mean by this loss of coherence also, right? So what does that mean? That basically means that for 10 to the 6 seconds, the signal will like nicely build up. After that, it sort of randomly drifts off to something else, right? So you can kind of divide your data, if you will, into these chunks and see coherence, 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 and then it sort of loses it. Yeah.
Even it was like this 10 to the 6 frequency, like
Oscillations, yeah. Yeah.
That's the maximum that we can have. It basically will be way
No, no, no. That's a minimum it could have. Okay, so I messed up my words a little bit earlier, but the point is this, right? Where does this come from? It comes from the fact that the minimum coherence length, okay, has to be, I think I messed up the sign here. It has to be greater than this, right? So the fact is, if the dark matter was faster, then the coherence length will be shorter. Exactly.
But is that I mean, it sounds like a bullshit, is that like a more systematic way to arrive at that?
Well, I don't think there's anything unsystematic in what I said. So my point was the following, right?
They are making use of the Heisenberg, right?
No, no, no. I'm saying the following thing. I'm saying that if the dark matter wave has to change, there has to be momentum in it. That is not a bullshit argument. That's just a statement, right? Then you say, look, given that I have to have momentum in it, okay, so what does it mean for this phase to become order 1 different? Okay, what you're now saying is that, look, I need to go x to x plus L. And when I go from x to x plus L, that is when a momentum k will cause the phase to change by order 1, right? So that's all that's happening there. Okay, good. Now there are, I would say, people in the field who are more optimistic, right? They believe in things like a dark matter stream, etc., which may be true. It could be the fact that like the dark matter that's blowing to us from Cygnus X1, which is the center of the galaxy or something like that, maybe that is more coherent than the typical dark matter, but I don't know, right? So it's possible that you may get, lucky and it's longer, but this is something you can bank on.
But if we make our detector large enough, can we see such stream behavior? Because it will have different kind of momentum and this momentum profile.
Yeah, so it's not really about it being physically large. It's more like temporally more stable. That in a sense you're able to sit there and wait for a long time, right? So it's really just a question of in time, how long does the signal actually last? Yeah.
Sorry, if you have a coherent state of electric field, you can have you can decide omega basically.
You can decide omega because you create it, correct? Yeah,
And k is c, I would say.
that's right. K is equal to omega, right?
Yes.
Yeah, correct.
Why in the case of that matter you cannot tune omega, you can have only one?
So the only person who can do that is the Almighty, right? So the Almighty created the dark matter, and the dark matter basically was picked through whatever mass was picked. Okay, so M is set in the Lagrangian, like whatever field it was, set the thing. What does happen then is the fact that because the dark matter is a massive particle, K and M are related by the velocity of the dark matter. For a massive particle, the velocity could be anything between 0 and 1, right? And what happens is that in the early universe, when you produce this dark matter, as the universe expands, its velocity will keep decreasing. So even if it had some initial velocity to begin with, it very rapidly goes to 0, okay? Then when you form galaxies structured in the universe, this velocity no longer is so constant because you're falling in the gravitational potential well, and so you end up getting randomization of this velocity. So what the argument then is basically saying, yes, I know there is some level of randomness, but I can limit how random it has become by saying that the most gravity can ever do is to give it an escape velocity, a velocity as big as escape velocity, which is 10 to the negative 3, but no bigger. And that tells me what the specific minimum requirements are. You had a question.
So what does this what do these oscillations look like plotted in this line, right? For 10 to the 6th stable oscillation and then something.
Yeah, so it's not like a dramatic jump, okay? That's a wrong picture, right? So, of course, everything is continuous, right? So a nicer picture to have in mind the following, right? Imagine you are, instead of sitting here, you're on a beach, okay? Something you might want to imagine, right? So then what happens is the fact that you're standing here and there are like waves coming at you from all directions, right? So of course, if you sit there and you're like figuring out how much water is going up and down your leg, right? It's continuous, the wave. But you will find, right, that basically this wave and this wave have no phase correlation. Maybe this thing came from a boat, maybe that thing came from a window, whatever. So you will find that actually speaking, for some time there is this nice coherence length. And it, of course, smoothly patches from one phase to a different phase. Okay? So that's literally what you see. But you can analyze it in that way. You can talk about it that way. You say, look, at least for this time, for order 1, that phase is well known, even though there's like noise in the phase itself. Does that make sense? Well, it is a, I mean, it sort of is like basically something that is, yeah, I mean, let's see, I mean, you have there's like, and then becomes like a longer term, I don't know, I'm probably drawing it poorly, like something bad like that, right? The problem is I'm giving you something in Fourier space and you ask me how to plot it in real time. Okay, and so you kind of have to do the inversion, but like the mental picture I want you to have is this experience of there just being 2 waves of the same frequency but different phases, and they interfere, right? So you will have, for example, structures of this kind that come from the fact that the different waves are interfering constructively and destructively at different points in time. Yeah. So it's like basically saying that there is dark matter from this side falling in, and there's dark matter from that side falling in, right? And essentially, one way to think about it is that the physical length of the dark matter particle is set by its de Broglie wavelength, which is 1 over mv, right? So in some sense, we are just saying that there is like one dark matter particle going through you at any given time. But of course, it's not one dark matter particle, it's like one mode of the dark matter field. And so that guy will take so much time to go through, and then the next guy comes in. But that's a little erroneous in the sense that it's not like it happens, one by one, right? They're all always coming. It's just that at any given time, because of this argument about what the velocity is, you're dominantly affected by one wave. And as the time peters out, you're getting more and more influenced by the next guy, right? So in time, it would look like something like this. There is some, nice little sign for some time. Then you get a bunch of constructive and destructive interference as those 2 waves become important. And then you kind of blend into the next thing. Yeah.
When you wrote absolute value of omega equals absolute value of k, you did not mean for the massive dark matter, you meant
For the photon.
Yeah.
Yeah. That's right. Yeah. Yes.
And what we also, so this is what dark matter from the photons, nuclei, and electrons.
Yeah.
What the other way around?
What is?
Photons, nuclei, and electrons can do to dark.
Oh, yeah, good. So those will be mostly questions about bounds, right? Like how do we? So I mean, practically speaking, for our experiments, it's not very important because like the coupling is so weak, right? But what you can twist that question around. You can basically say, how does the dark matter affect the standard model? That's what you're asking, and those are all limits on this stuff. And indeed, what it can do is pretty much the opposite of all these things, where basically the photons, for example, if you're in a star, right? Electrons, protons, and photons, they can come together, they can scatter, they can produce dark matter particles. So that will give rise to certain kinds of limits on dark matter. The relative motion of baryons and dark matter over here, for example, so this is a nice example, right? Just like how the dark matter can move baryons can also move dark matter, right? And what that would do in the early universe, if such a thing actually existed and it was big enough, is that it would cause damping of the growth in the dark matter fluctuations, right? So in the CMB, we kind of see the fact that there is the 2 fluids, right? There's a photon and baryons coupled together, and then there is basically the dark matter structure. And if you've got like friction between the 2 of them, it can affect the growth in the dark matter structure. So those are all like bounds that you have on what the dark matter can be, or how strong its interactions can be with the standard model. And essentially, we are now in a situation where we are, if the bounds were significant, right, if they were strong enough, we would have already seen them, and we have not. So in some sense, we are now in the limit of like, well, they don't influence each other too much, which is why you have to work so hard to detect it. Okay, very good. So for me, that's the point, right? As an experimentalist, you can just think about the observable effects and go with it. But we should also ask, theoretically, right, which of these things are reasonable things you can get or easily get in theory? And it's also worthwhile, in my opinion, to understand at least which of these give rise to technically natural interactions, as in like, is it reasonable that the dark matter could have an interaction with a photon and cause it to change its polarization and still have a mass as small as 10 to the negative 22 eV? Or is it, do you have to be like super lucky to get something like that, right? So we'll do the theory motivation. I'll push this up. This comes to now asking, what are the theories of dark matter that give rise to these effects? Okay, and we will also demand technical naturalness. All right. So if you want to talk about technical naturalness, there aren't actually very many ways that we know of in which things can be technically natural, right? Like this is why we have a hierarchy problem and things of this kind. So for scalar fields, there is a well-known technique, okay, which is called the shift symmetry. Now, I don't know how many of you are familiar with it, so we'll just briefly discuss how these things actually work in practice to see what's going on, right? So let me write down, I guess, 3 interactions for scalars, okay? And I'll let you guys decide which ones are good or bad from the point of technical naturalness. So let me write down this coupling phi, psi bar psi. Phi is my scalar, psi is a thing, a fermion. And then let me write down d mu phi, psi bar gamma mu psi, and then d mu phi, psi bar gamma mu gamma phi psi. Okay, so given the psi and gamma mu, I can write these 3 things with some leading order terms I've written down. Okay. Now, looking at this, is there a term that you want to knock off immediately? Is there a term that you want to knock off and say, well, that term can't possibly be relevant?
Maybe the last two, because it has more than 4 dimensions, so it's literally probability 4.
Well, I mean, that just means there's a cutoff, right? So there's basically some scale where you're right, there are high dimension operators, but okay, I mean, so what, right? So what? I mean, gravity is not UV complete, right? It doesn't prevent it from existing. So we're taking the very effective field theory point of view, where we just say, look, there is some scale, physics at the scale lambda. I don't know what it is. It's what I'm trying to find, and this is a way for me to detect it. Yeah.
The second last character is what? Gamma subscript.
This one?
Second last character.
This one, gamma 5.
Gamma 5.
Yeah. The first. You don't like the first. Why?
It generates a mass
Okay. So what you're saying is that if I have this phi, psi bar psi, it generates a radiative mass, right? Basically, he's saying that I want a technical naturalness. So I was basically going to be like saying, look, if I have this phi, then I can draw some loop of psi, and then this will give me a mass, like the Higgs boson, right? Like one of those things. Okay. Why are you so sure that these terms will not generate such a mass? Is the d mu. Okay, can you elaborate on that?
potential is defined as zero momentum.
Okay. Yes, but I could have thought, right? Like, who knows? I mean, I wrote this, but maybe I could have, actually computed this thing in more detail and put in all the derivatives, etc. And I might indeed, at the end of the day, find that there is some non-zero mass at some loop order or whatever, right? There's a lot of algebra that you're not actually telling me about. So what is a way in which I can prove that these terms cannot possibly generate a mass? Shift symmetry, right. So I already sort of said the answer, perhaps, right? So what is the whole point here, right? We're basically saying, look, I have these terms, and there could be a very complicated set of interactions, lots of diagrams that you could draw, etc. And what you're asking is basically, you're looking at this Lagrangian and you're saying, does this Lagrangian have some kind of symmetry? If it has some kind of symmetry, you can use the existence of the symmetry to preclude the possibility of other operators that break that symmetry. Okay? So what you realize is that for these two terms, I can send phi to phi plus some constant c. When I do that, the derivatives do not change. Right? So these terms, okay, this guy and this guy, they are invariant under this shift symmetry. And the whole point is, if the field had a mass, the mass would not be invariant under that shift symmetry. Because if I write down a mass, m squared phi squared, right? When phi goes to phi plus a constant, this term changes. M squared phi squared will go to m squared times phi plus constant, the whole squared, which obviously is not m squared phi squared, right? So what this argument tells you is that when you have a certain symmetry property of the Lagrangian, then you can use that property to rule out the possibility that quantum dynamics will generate certain kinds of operators that break that shift symmetry. So we would say, okay, this guy is not protected by this kind of shift symmetry, whereas these guys are protected with the shift symmetry, and therefore we would say this guy is not technically natural. But these guys actually are. Okay? Now, by the way, I did mention this yesterday. Yes, if you have a field that violates technical naturalness, there is a theoretical question that you must be asking, right? Like, is it reasonable 10 to the minus 22 EV or not? But from my perspective, experimentally, we should not stop looking for these things, since the experiments we talk about don't cost too much money, right? Because this is an important point, which is the fact that our world is technically unnatural. The Higgs boson, technically unnatural. The cosmological constant, technically unnatural. And that doesn't stop those things from being true, right? So it all comes down to for me, a question of cost and effort, right? If it's like a $100 billion thing for 100 years, okay, don't look for technically unnatural things. Maybe not a good idea. But if it's a few million for a few years, why not? Okay? So I will still retain this thing as a term we will be interested in, just to see whether it is, that difficult or not. And in fact, we will find that it's not too difficult to find it. And a similar phenomenology will also appear from other fields we'll be interested in, which could be technically natural. But I want to focus on these two terms now, because they are technically natural. Do they both exist? Do they both give rise to interesting physics?
Depends on the source concentration and how it acts under C or CP.
Well, I mean, yes, they may break CP or whatever, but so what? There's one term, I'll even sort of, so I'm asking, like clearly when I'm asking you, there's something wrong with one of the terms. So what is wrong with one of the terms? Yeah. Okay, pseudoscalar, scalar, fine. So what? So what? How many of you have seen this term written down?
When there is gamma, I'm not an expert, but when there is gamma phi, it's not spin related.
Gamma phi is spin related. Okay. Have you ever seen this term ever written down? You have. Well, okay, so the point is this, right? Like, remember, to be a successful theoretical physicist, there are two things you need to know. You need to know taking Taylor series, you need to know doing integration by parts. Okay, those are the only two fancy mathematical tricks you need to know. And now do an integration by parts. Okay, you should always be able to do that. What does that give you? If you integrate this by parts, you get phi d mu psi bar gamma mu psi. The minus sign, yeah, fine. Okay, but this is identically zero because of fermion number conservation. Right, psi bar gamma mu psi is your, if it's a proton or whatever, is your baryon number, your charge conservation thing. So this term does not generate anything interesting. Okay, it can for like particles that can mix with each other, like neutrinos and stuff like that, where something non-trivial can happen. Okay, so even though we kind of scoffed at neutrinos, because they're just hard to detect, right? There's potential maybe for something of this kind where the number is not exactly conserved to see what might happen there. Okay, but for electrons, protons, and neutrons, because those numbers are individually conserved in any experiment, this term will be zero. Okay, so we only therefore need to focus on this operator d mu phi bar gamma mu gamma phi psi. Okay, so let's make a list of operators. I will write this on top of this here. And we will say, natural and unnatural. And the naturalness line here will be d mu phi psi bar gamma mu gamma phi psi. And the unnatural term is phi psi bar psi. Okay? There is another term I can write for the scalar, which is the term phi, let's call it E dot B. Okay? That is Kira's term from yesterday. Okay? Is that a technically natural interaction? Is that shift symmetric? No, right? Because clearly, when I send phi to phi plus a constant, that term changes, right? It goes to phi plus a constant E dot B. Okay? So it looks like it's not shift symmetric, but that's an axion term, right? And everybody in the world loves axions. Okay? So why would that term be okay if you're a person obsessed about naturalness and all that kind of stuff? Huh? Yeah. There is a what? Well, see, the question of what this field is in the real world, right? Basically, a statement about what classical field I'm having. That is a statement about what quantum state phi is in. But here we're talking about it from the level of the Lagrangian, the level of the operator itself, what lives in the Hamiltonian, basically, right? So these are just the constructive fields itself. So it's not because of phi being a, so like, you should think about it not from the perspective of this being a specific dark matter field. We're just talking about the fact that at the level of the operator, this is what actually happens. So once again, use integration by parts, right? That's one of the two things the theorist needs to know. And what you can do is you can write the electric field as a gradient of A naught, the potential. Okay, and then so what you want to know is this, right? So this is still phi E dot B, that has not changed. So now you go to a constant, and then you get a gradient of A naught dotted into the magnetic field. Okay, let me now do integration by parts. So this term doesn't change, I'm not doing anything there. So this becomes negative, okay, of A naught del dot B. Okay? And if we live in a world where there are no magnetic monopoles physically present, del dot B is 0. Okay? So that means that even though this term formally looks like it is not shift symmetric, it secretly is shift symmetric, because what we've learned is that this term identically vanishes. So when I do the shift symmetry, phi goes to phi plus c times E dot B, but the C E dot B has no physical effects. Okay? And so it goes away, so this is invariant, and so this also gives rise to a technically natural scalar called the axion, which people look for, and that is, we can put that in this coupling, phi E dot B. Okay? The next coupling that I will write, okay, is for the gluons. Phi GG dual. And this, if you expand out in gory detail in QCD, this becomes phi, the color electric field EA dotted the magnetic whatever. I'm probably even screwing this up. There's some complicated QCD way of writing this thing, but I think that's what it is, right? Now, that term also naively looks like it is not shift symmetric, right? Phi goes to phi plus c, it changes. But once again, you can do exactly the same trick, right? You can say that, look, when I do this thing, phi goes to phi plus c, this changes to phi plus c times this EA dot BA. And once again, there are no color magnetic monopoles either. And so you can perform the same trick, which will allow you to say that this term, this C is also physically irrelevant. Okay? This will turn out not to be completely true because it's something called the strong CP problem. And I mean, I'll discuss it at some point in some detail. Okay? But there is some version of the shift symmetry that still remains here, which can also keep it light. Okay? So when we discuss the strong CP problem, I'll get into more detail on exactly what it is. So we will still put that here as well. So this is again phi GG dual. That's the term. Okay? The other kind of interaction you could write down, which is also technically natural, is you can make use of the fact that the Higgs particle, and I can write down this coupling small g phi Higgs squared. Okay? Is that technically natural? You say no. Okay. Why? It is definitely not shift symmetric. Okay? But it is sort of in some sense secretly okay. Okay? And it is for the following reason, which is that you can ask, if I have this coupling g phi Higgs squared, okay, and I want to distinguish that from, let's say, a coupling lambda phi psi bar psi, right? This one we all agree lacks shift symmetry, and we all agree that would be bad. It would give rise to a quadratically divergent mass, right? So it looks like naively these things are similar, okay? But there's an important difference, which is the fact that this G has mass dimension 1, whereas this guy is dimensionless. Okay? So what does that mean? It basically means that if I draw some loop and I want to know what mass is produced by the loop, right? I have to use this G twice here. So for example, here I have a phi, Higgs, Higgs, phi. So there is a G here and the G here, right? Whereas for this guy, this is basically a fermion thing. There's a lambda, there's a lambda. These guys are dimensionless. So when I ask, what is the correction to the phi mass from this guy, this will go as lambda squared times some cutoff. Dimensionally, that's what happens. Whereas on this side, you've got delta m phi squared. I have to use 2 g's. But the moment I use 2 g's, I've already got mass dimension 2. Right? So there's no possibility for the quadratic divergence to arise. And you can calculationally see it. Calculationally, what you would do is you put in the fact that I've got 2 bosonic propagators here. and then calculate what happens, you will find that this actually goes as g squared, whereas in this case, these are two fermionic propagators, and they scale differently with momentum, and that's why you get a quadratic divergence in one case and no such divergence in the other case, right? But from dimensional analysis, you can quickly see why this is technically natural in the sense that if g is small, the mass will remain small, okay? So we're going to put that here also, g phi Higgs squared. That means if I start with the parameter that I put in as small, the physical mass that it generates remains proportional to what I put into it. That remains small. There's no like UV thing coming and making it big. Okay. So all of these are the different operators. Yeah.
So I would just add, there is a d mu psi bar I, gamma mu psi j.
Uh,
If you do like a mu to e gamma. Right?
yeah, if you change flavor, yes. But I'm sticking with the first generation. Right? Yes. So I think there's a very interesting question, okay, which I don't know the answer to, which is like we've listed these things because these are the things that we dominantly control in our lab, right? And so we can ask, well, what about particles coupled to muons? What would you do there? So that's a separate story. Yes.
So when you're saying that G is small, what scale are you saying it's small compared to? It has a mass scale.
Yeah. So G is the mass of the particle itself, for example. Right, so like when I say that the mass of the dark matter is 10 to the, so yeah, good. So right, so these things will give you a mass for phi that's order g. So I would take that to be the scale of whatever comes up. So all of this is for spin zero particles, right? But we can just as well talk about spin one as well. There could be spin one classical fields like the photon. And so why don't we think about massive spin one fields and see what they can be. Okay.
Can you make yourself clear that? Can you?
Okay.
So when you make P to P plus C,
Yeah.
they have the term which makes it not shift.
It's not shift symmetry. That's right. So protects the mass of phi in this case is not a shift symmetry. It's rather the statement that it's a specific kind of coupling. It's like this dimension 3 interaction, which means that there is a mass generated. The mass, however, is proportional to g squared, right? So now, right, so in some sense, right, like the mass for this guy is proportional to lambda squared. That's also true. But the point is there's now a new scale in this case, the cutoff that comes in, which has no opportunity for showing up in this case. Yeah.
So you define the shift symmetry, or it's generally defined. Shift symmetry is something which doesn't mess with the mass. Or any property of the Lagrangian.
Right. So a symmetry means you do it, it shouldn't change the Lagrangian at all.
Yeah.
Right?
Now in this case we only look at mass. What if it alters some other physical variable that we may be interested in?
Well, the thing is, yeah, so what we're saying is this, right, that basically when you have the shift symmetry, the Lagrangian never changes, which means it cannot generate any term in the Lagrangian, a mass, a quartic, anything, that is not invariant under shift symmetry, right? So for example, if I give any of these operators like d mu phi, psi bar, gamma mu, gamma phi, not only does it not generate the mass, it also doesn't generate a quartic of the form lambda phi to the fourth or phi to the sixth, any of those kinds of terms. Same, exactly. Yeah. Yeah.
To be technical, since we've made a couple integration by parts arguments, it's not the Lagrangian that is unchanged, but the action function.
The actional function. Yeah. That's right.
Can I solve the Higgs Higgs problem this way?
Can you solve the what?
The Higgs hierarchy problem.
Well, that is a relaxion, right? That's the part of the idea. Yeah. So yes, you can solve it, but but it's not just with it. It's a longer story. Yes.
Yeah, we can tell G square, and so we said that we cannot relate
Yeah. So the actual hierarchy problem, right, is a sort of a different thing, where you might say that it really is because of the fact that we know the Higgs has other interactions, like it has it sort of interacts with the top quark, right, which of course is not that form. The top quark is, say, lambda Higgs, whatever, right? So there's a Y top Higgs QU. This guy generates a mass for the Higgs, right? So that is the mass you need to kill. And just by adding g phi Higgs square, you don't kill that mass. which is why you need to do the fancy relaxion style things. Okay. All right. So let's talk about spin 1 particles and do a similar classification. Okay. For spin 1, that means what? That basically, let's say there is a gauge field B mu, right? So we are used to the electromagnetic field A mu, and we define it by having an F mu nu, which is some D mu A nu minus D nu A mu. And the Lagrangian for the photon is basically negative F squared, and then it couples to some charges, right? Some E, A mu, J mu electromagnetism. So that is QED that we deal with. So we're going to say there is something called the dark photon, the hidden photon, various photons of that kind, right? And the idea is this. We're going to say there's a field B mu. I'll, let's say, define an E mu nu, which is its gauge strength, D mu B mu, B nu, minus D nu B mu. And I will say the Lagrangian of the dark sector contains a negative E mu nu squared, just like this is a negative F mu nu squared. And then comes the question of how can we make this B mu interact with the standard model? Okay, what are the technically natural things you can do, and what are the technically unnatural things you can do? Okay, so one term I can write down right now, and also there's a mass. Sorry, there's a mass. There's an m squared B mu squared, right? So that's how it is distinguished itself from the regular photon, because it has a mass. And what we want to know is basically, look, if I give this B mu interactions with the standard model, those can also now potentially radiatively generate, through quantum corrections, a large mass for B mu. So it's possible that I'm not technically natural anymore. But I'm interested in asking what are the interactions that I can write down that preserve technical naturalness, right? What are ways I can do that?
Can you, whenever you use terminology naturalness and technical naturalness?
Oh, I mean that they're the same.
Okay.
Yeah. Okay. All right. So let's think about some possible things I can write down. I could write down this coupling. Let's call it epsilon, okay, F mu nu, E mu nu. Okay, that's a term I can write down. And what you can notice now is that when I write down this term, this actually still maintains some kind of gauge symmetry or shift symmetry. So first, actually, before we get here, we should understand how is it that the photon can interact with electromagnetism, right? Like with an E mu, J mu, and still remain massless. What symmetry is used there? That's the usual gauge symmetry. So we'll talk about that for a second and then see how the exact same thing can be applied for the hidden photon as well. So why is the photon massless? That is because you now have an A mu, you say, which goes to A mu plus D mu alpha. When you do that, F mu nu goes to F mu nu, because you send your D mu alpha in there. You've all seen this before. It doesn't change. This term will change. This term changes to A mu plus D mu alpha times this J mu electromagnetism. So it looks like it changes, but once again, you do integration by parts, right? You integrate this term by parts. This becomes negative alpha D mu J mu electromagnetism, and the electromagnetic current is conserved. This term is 0. Okay? So what we have therefore seen is that this Lagrangian is invariant, okay, when because it is invariant under this kind of gauge symmetry. But it's also like a shift symmetry. That's actually what's going on. Okay? So what we now want to see is basically the exact same logic being applied to this sector also, where we would now say, look, given this B mu nu, I can have this B mu goes to, let's say, B mu plus some D mu beta. And under that, E does not change. And so if I look at this Lagrangian, this term is invariant. This term is invariant because F doesn't change under B at all. F is invariant under alpha, and E is invariant under the shift as well. So the only term that breaks the shift symmetry, this gauge symmetry here, is m squared B squared. That's okay. right? Because if the mass vanishes, it would go away. So whatever mass you're getting from this interaction is proportional to m squared. Okay? So this term is a technically natural term that I can write down. So I will put that on this side as well. Because all of this is spin 0. This is a spin 1 sector. This is spin 1. And I can write down epsilon E mu nu F mu nu. That's a term I can write down. Okay? The other possibility is that, so this thing, by the way, is called kinetic mixing because there's the photon field mixing with this guy, right? That's a possibility. The other thing we can talk about is whether or not, just like how the photon directly talks to charged currents, protons, electrons, and neutrons. It doesn't talk to neutrons, but talks to protons and electrons. One can ask, is it possible that the B mu directly interacts with standard model particles, right, like protons and electrons? And there comes the question, in what way can I interact with these guys and still remain technically natural, that is, still have a small mass? So what we have to ask is basically, what currents can I write down? Okay, I want to put in some coupling, let's call it delta B mu, and there's some current J mu that I want to write down here, and I want this entire Lagrangian to be invariant when I perform the shift symmetry, where I'm sending B mu, or this B mu to B mu plus D mu beta. So then I will have a change that this thing changes by delta B mu plus D mu beta times this J mu. And so you want some way in which I'm coupling to some conserved current so that this thing doesn't change. So you got to ask, given the structure of the standard model, what kinds of conserved currents can I put there? Okay, and this is a long technical topic having to do with something called a quantum anomaly, which you may have seen, where you basically ask, there could be some currents that you write down that naively look like they are conserved at the classical level, but quantum mechanically they are not, right? There are these triangle diagrams that you can draw, these charges that show up there. So there's a classification of this, which basically show that there are, various versions of baryon minus lepton number, okay? It's not just one, there are 3 or 4. I think Urey knows them better. So there are various versions of baryon minus lepton number conservation currents, which are all conserved. Okay, L mu minus L tau, various versions of this kind. But I'll just give us like an example, since I'm mostly interested in the first generation. So I can write down this coupling, okay, which is basically this B mu. Let's call it J mu B minus L. Okay, what is this, right? So under electromagnetism, okay, we have the following facts, that under electromagnetism there's an electron, there's a proton and a neutron. Under electromagnetism, the electron has charge 0, the proton has charge, it's charge minus 1, the proton has charge plus 1, the neutron is neutral, right? And the neutrino is also neutral. Under B minus L, okay, the electron is negative 1, the proton is plus 1, the neutron is plus 1, and the neutrino is minus 1. Okay, that's another charge assignment that you can actually give that's consistent. Okay. By the way, could I think of a charge assignment, okay, where, because we're going to play some games, right? Because it looks like I just wrote down some numbers. Okay, so I want to know what truly restricts this. Could I have, for example, given you a scenario where, let's say, the electron has charge 0, the proton has charge, let's say, minus 1, neutron has charge plus 1, and the neutrino has charge minus 1. Huh? Well, I want to know, right, like what restricts these charges. So we all know the electron has charge negative 1, and that seems to be okay with the world. And what I'm asking is basically, could there be a new gauge boson, a new force, okay? And I asserted that this one is okay, minus 1, 1, 1, minus 1. And you all listen because I'm speaking about this with great authority, okay? But if I had instead said 0, minus 1, 1, minus 1, with the equally good authority, what would you say is not possible? Well, before we even get to the anomaly, okay, before we even get to something as complicated, what other interaction in the world that we know about would, poo-poo that immediately?
Electron and proton should attract each other. In that case, it doesn't.
What is?
Electron and proton should attract each other. In that case, they don't.
Well, so what? Yeah, it's another force. Yeah. Someone said something that sounded right. Yeah. So what? I mean, if the coupling is small, it could do it, right? The neutron attracts neutrinos through gravity. Yeah. Uh-huh. That's right. So we know for a fact that in our world, neutrons decay to protons, electrons, and the antineutrino or whatever, right? So that process happens. So that means charge has to be conserved there. So if you assign things of this kind, that's not possible. Okay? So that's one of the reasons why you can't put in random numbers here, right? There are, whatever it is you need to put in has to work with the charge assignments allowed in the standard model. So that's already a restriction. And on top of that, there is also the anomaly restriction, which tells you that, yes, there are only certain combinations that actually work. So one combination you can have is with this B minus L. So you can have this coupling, let's call it like some, it's B mu, J mu, B minus L. Right? So all of these are technically natural. Okay? One can also go a little bit beyond this and say that, look, I know that the various standard model particles, like the neutron, okay, the neutron has a magnetic dipole moment. Okay? It can also have an electric dipole moment. We will talk about that, I guess, in the next lecture now. So those operators are also possible. And that is because in the standard model, I can write down terms of this kind. F mu nu, psi bar, sigma mu nu, psi. Okay? And then F mu nu, psi bar, sigma mu nu, gamma phi, psi. So these things give you magnetic and electric dipole moments. Right? So even though the neutron is not charged under the photon, the neutron is not attracted by the photon, nevertheless, if I apply a magnetic field, the spin can precess. Okay? So similarly, we could imagine, and this, by the way, also is automatically gauge invariant because I just have this F mu nu come in there. F mu nu is gauge invariant. These guys don't care. So similarly, it could be the case that under the dark gauge boson, once again, that the neutron, electron, proton, these particles may have dipole moments. So I could write down a coupling of the form E mu nu, psi bar, sigma mu nu, psi, E mu nu, psi bar, sigma mu nu, gamma phi, psi. Okay, so I can write down those terms. E mu nu, psi bar, sigma mu nu, psi, E mu nu, psi bar, sigma mu nu, gamma phi, psi. That's a possibility as well, and they're all technically natural. Okay. Now, one term that we could have written down, which which I'll write down now, which I didn't do earlier, is that I forgot something about the. So far, we have focused on the fermions a whole bunch, and not too much on the photons. So there's one particular term also that you can write down for photons, which is the term phi f squared. So we wrote down phi E dot B, which is for the axion phi f mu nu, something called f mu nu dual. And f mu nu dual is this epsilon mu nu lambda sigma f lambda sigma. Okay, that's what it is. But this is the regular f squared. So this is just phi f mu nu f mu nu. And that just directly couples the photon to E squared minus B squared. And this term is not shift symmetric, unlike this term, because now if I send phi to phi plus c, my Lagrangian changes to cf squared, okay? But cf squared is physical. It's a kinetic term of the photon, okay? So that term will generate radiative corrections, but nevertheless, it's a possible thing, so I can put that here. There is a phi f squared that I can write down, okay? So I will just mention this quickly, just to wrap up the discussion, and then we will take a break, and then, yeah.
Just to add two more that are maybe weird, but I guess natural, you could also have a charged particle with 10 to the minus 20 charge, as long as it's 1 over 10 to the minus.
Oh, yeah, like an ultralight scalar charge. Sure, that's true,
And
yes.
also, similarly, a dark boson that just directly, the standard model is charged under, right?
Right. Yeah, no, absolutely. My goal right now is to basically be like, I've got these observational possibilities, right? And in fact, actually, yeah, the charge boson you're talking about would be a way of getting an index of refraction, right? So I'll write that. I guess it would be technically unnatural, but so what, right? Because of this charge. It's a charge boson, right? That's what you have in mind,
Yeah.
right? So
It is technically natural.
technically unnatural, right? Because the charge can give it a mass. Huh?
I mean, it's a tiny mass if you put a tiny charge.
Oh, that's right. So that's true for all these cases, right? If I give you a, yeah. Yeah. So indeed, as Itai is saying, I could also give you a boson that has a charge, right? Now that's a kind of a, so you have like a positive and negative charge sitting on top of each other. It would be a plasma that you can have, but that's certainly true. So I can just give you like a, I mean, there's no specific coupling I'm going to write down. It's write as a mu, let's call it like phi star d mu phi minus, phi d mu phi star, okay? It's a small charge. But that's a, assuming the dark matter has an epsilon charge in the world, okay? So I'll just assert some claims, and then we can see in detail how they work in the next time. So here is my classification of physical observables, and here is what the theory will give me, okay? And let me just quickly say what does what. So this term, d mu phi, psi bar, gamma mu, gamma phi psi, that term and these guys, e mu nu, psi bar, sigma mu nu psi, and e mu nu, psi bar, sigma mu, gamma phi psi, these guys have to do with spin, okay? So what this term and this term will do is that they can induce spin precessions for nuclei and electrons, okay? This term, a b mu, j mu, b minus l, right? That is something where you're directly exerting, you're assuming standard model particles are charged under b minus l, so there's a force, it'll directly act on it. Similarly, this unnatural guy, phi, psi bar psi, it can also exert a force. Phi f squared can also exert a force, and so can g phi Higgs squared, okay? So this guy, this guy, this guy, and this guy, they can all move nuclei, okay? In the case of the photon, we have the fact that basically this term, phi e dot b, this is the term that Kira was talking about yesterday, okay? And also in some way, this epsilon e mu nu, f mu nu, both of those can mix with the photon and create some electromagnetic field, okay? Similarly, phi e dot b can change the polarization of photons, okay? And phi f squared, it turns out, okay, so this is an interesting fact, all right? So you correctly mentioned that theoretically it's possible, right, for a photon's direction to be changed by something, okay? Now, yeah, maybe we'll just finish with that discussion. So I still have to tell you what we can do with these two guys, okay? And indeed, the last one, which is an index of refraction, is exactly sort of Itai's example, which is that I can give you a dark matter that has a small charge that will do this, okay? But let me kind of just make an interesting point about whether or not it is easy or difficult to change the direction of a photon with something other than gravity, okay? Light of any kind, coherent state or even photon particles, massless particles, okay? So this is a last topic before we stop. So I want to affect the motion of photons, okay? And the only game in town that's around is this term, phi f squared, okay? So we have phi f squared. The question is, does phi f squared actually cause a photon's direction to change. So let me give you an example of how it could, right? So maybe, right, phi could be sourced by some fermion density, okay? So what's happening is that I have the Earth, and the Earth creates a phi field around it. And then you might say, if I actually have a phi f squared term, then when light moves by, there's a Feynman diagram that would be like, oh, look, there's a phi being exchanged, and that should cause the photon to bend. Okay? Turns out this is not true, because f squared for a photon, well, f squared, no matter what, is e squared minus b squared. Okay? And for a propagating photon, e squared is equal to b squared. So phi does not actually couple to massless photons. Okay? It doesn't cause the bending of light. So this is historically important, because before Einstein came up with general relativity, there was a guy by the name Nordstrom who came up with Nordstrom's gravity. And what was Nordstrom's gravity? So the whole point, right, was basically they were asking, look, I know Lorentz invariance is correct. I know electromagnetism is automatically invariant under sort of Lorentz transformations. So how do I construct a theory of gravity that is also invariant under Lorentz transformations? And the naive thing you would have done, right, is that you would have said, look, what gravity did I know back then? I knew the gravity of Newton. But all I know is that there's a scalar force that is exchanged between particles. Right? The Newtonian potential that we see in our world is a scalar. So the naive thing you would do before going and doing all fancy pants GR is to basically be like, well, why could I not write down a scalar analog of gravity and try to make it Lorentz invariant? Right? That's a naive thing, and that's what Nordstrom did. So what Nordstrom did was write down exactly a scalar theory of gravity where he put down the coupling phi f squared. Okay? Now, there are issues of naturalness, etc., in this theory, but some of it you can even address. But the ultimate problem with this theory, experimentally, and the way it's distinguished from GR, is that in Nordstrom's gravity, light will not bend. Okay? Whereas in Einstein's theory, what happens is that I actually have the coupling of light is to the metric, right? There's a g mu nu, g alpha beta, f mu alpha, f nu beta. So the way the indices are contracted, you're not coupling to e squared minus b squared. So a spin 2 degree of freedom is able to bend light, whereas a Lorentz invariant spin 0 does not actually cause the bending of light. Okay? So that's an important difference. I don't know of a Lorentz invariant way of doing that specific thing, but that's interesting for other reasons, which we'll see if we get there or not. Okay, so with that, let me stop. Right. So what I've told you today is the fact that I am interested in asking. There's some classical field in the world, and I can simply ignore all theory and just simply look at what I can do experimentally to various particles. Okay, so that's just a classification based on what's in the world. And unsurprisingly, it is the case that for every one of these possible physical effects, except for the bending of light, one can write down Lorentz invariant quantum field theory operators that generate it. Some of those effects may require you to violate technical naturalness, but I'm okay with that for now, right? Because that's a job for the theorist, not so much for the experimentalist. And ultimately, if you want to detect any of these physical effects, all you're going to be doing is by saying, look, I'm going to take every one of these operators, okay, and for the dark matter field, substitute the classical dark matter field that you have, some phi naught cosine omega t, and then be like, okay, I've got a phi naught cosine omega t sitting here, and then analyze how my particles, the photon, electron, proton, how do they behave in the presence of this classical background. And that will tell me experimentally what's going on, and then we can think about experiments that detect it. Okay? So with that, let me stop.
Any question?
Yeah.
So the Lagrangian, so like real quick, so it was like phi f squared is because a propagating wave would have f squared equals 0.
Yeah.
Yes, this term the Lagrangian goes to 0. Does that also mean that the equation of motions it generates some problems?
Yeah. So good. So actually, since I sort of mentioned a little bit of the amplitude and all that, we'll just talk about it right now. Okay.
Sorry,
for a propagating wave. Because E squared is equal to B squared.
Right.
Okay. Yeah. So let's just do it. Okay. So if you obtain the equation of motion for this guy, right? What's actually happening is this. How do you obtain the equation of motion? You have phi f squared, and this is basically d mu a nu minus d nu a mu. And once again, you use your integration by parts. Okay. When you do integration by parts, notice the following thing happens, right? So this becomes d mu a nu minus d nu a mu squared. Or actually, you know what you're going to do. Like, you'll just go to the Euler-Lagrange equations. You can just do that, right? So the Euler-Lagrange equations will tell you that the equation here is a d mu, dl, d, whatever, d mu a nu minus dl, d a mu equal to 0, right? That's the equation of motion. This term, of course, vanishes for the simple term that we've written down so far. So what you now see is that you now end up getting a term which is like a d mu, and when I have this dl, d mu a nu, I end up getting a phi f mu nu here. Okay? So this term becomes of the form phi d mu f mu nu plus a d mu phi f mu nu equal to 0. All right? So I can now divide by phi throughout, and this becomes a d mu f mu nu plus d mu phi over phi f mu nu equal to 0. Okay? Now, this is the part that I'll be quick about, but you can verify this. So you can ask, okay, when I have this term d mu phi over phi, what does it do? So it's not that phi doesn't affect the photon, okay? But what does it actually affect, right? The one thing I want you to notice is that this term looks like a frictional term, right? It's got like a phi dot that multiplies something, okay? So what actually happens is the following, right? You can say that take your photon wave and you go into what is called the iconal limit, okay, which is the argument that you say that the frequency of the photon is very large, the wavelength is very small compared to the background field you're propagating in. And in that limit, you will find that the geodesic motion of the photon, which is what you're typically measuring, is governed by this term, which is unchanged. However, the amplitude, which is basically talking about how many photon particles are actually changing as a function of time, that is governed by this term. So this is quick, so we can do it more carefully later. But that phi f squared, even though it doesn't affect the bending of light, what it does do is it affects the amplitude of light. It sort of controls how many particles per second per flux that I'm actually going.
We have not invoked t squared minus b squared equals 0.
No, not in this. So that's a quick way of saying why it is, but the equation of motion is the right way of doing it.
Because the photon converts into scalar.
No, well, I mean, okay, I wouldn't say it's conversion. It's not really a conversion, right? Because like a propagating photon really cannot convert to a phi because of the mismatch in energy and momentum. Because phi has a mass and it doesn't.
But where does the number of photons go?
So it's a question of like how when phi changes, right? Like it's a statement of what is called the volume element of the photon that actually changes. It's like it's a question of like, when you say you want to talk about how many photons per unit second or some centimeter cube, right? So what defines that? So this phi has that job. It defines the volume element. Yeah.
If I remember correctly, I think that non-linear gauge theories can also be technically natural.
Yes.
We also have assumed that for our task.
We could do that as well, but you're correct, right? So the thing is, non-abelian gauge theories, to write down gauge invariant operators that mix with us, they are all even more higher dimension. So it is an open problem, right? So it's not like there is a fundamental reason why the dark matter has to be U1. It could very easily be non-abelian. And the thing is, you now write down these operators. So these are all like dimension, like 4 and things of this kind, lower order. For non-abelian, everything will be even more higher dimension. So it is just a very, very hard, and I would say open problem to figure out if the dark matter is something non-abelian of this kind, how could we detect it? I don't know the answer to that. One more question, I guess. Yeah. And then
consistent and up to which scale having massive Higgs boson?
yeah. So if you actually have a massive gauge boson that interacts with this kind of interactions, it is technically natural. The cutoff can be arbitrarily high. The cutoff can be arbitrarily high.
The theory is consistent up to n scale
Yeah,
because it's a billion.
of course it's a billion. Yeah. So in a sense, all this gauge invariance we have taken care to protect, to write down, protects it. Right. Thank you.